Calculus was first discovered by Isaac Newton and Gottfried Leibniz. However, both of them had very different concepts of calculus. Newton considered variables changing with time, while Leibniz thought that the variables x and y ranges over sequences of infinitely close values. Leibniz suggested that dx and dy as differences between successive values of these sequences, and that dy over dx will give the tangent, although he didn't use it as a defining property. Newton, however, used quantities x prime and y prime, which were finite velocities, to compute the tangent. The both of them never thought in terms of functions, rather in terms of graphs. Leibniz put in a lot of thought in terms of good notation and symbols used. On the other hand, Newton changes notation and symbols based on what he felt like using that day. As a result, most of the notations and symbols used by Leibniz are still being used until today. This is because they were better attuned to generalizing calculus to numerous variables and also highlighting the operator aspect of the derivative and integral. Today, we call it the Leibniz notation.
The Leibniz notation can be applied to many mathematical functions, including trigonometric functions, exponential functions, and logarithmic functions. Sinusoidal functions are functions that contain sine waves at a periodical fashion. Leibniz notation is used to find the instantaneous rate of change of a sinusoidal function. In other words, the tangent line of a sinusoidal function. To find the slope of the tangent line, the function has to be differentiated and an x value must be given. For example, to find the slope of the tangent line to the graph of fx equals to 3 sine x with an x value of pi over 4, differentiate the function so it becomes 3 cos x. Then substitute the x with pi over 4 and it becomes 3 cos pi over 4. By using the idea of the unit circle, the slope at x equals to pi over 4 is 3 times 1 over square root of 2, or 3 over square root of 2. By graphing a sinusoidal function, the local maximum and the local minimum can be identified when the derivative of the function equals to 0. When sine x is differentiated, it becomes cos x, and when cos x is differentiated, it becomes negative sine x. There are various rules that can be applied when it comes to differentiating sine and cosine functions. The constant multiple rule, where a constant can be extracted from the differentiated component. An example would be that when y equals to 2 sine x, 2 can be removed when the function is being differentiated, so it becomes 2 times dy dx sine x. The answer would be 2 cos x. The sum and difference rule, where the derivative of f plus or minus g equals to f prime x plus or minus g prime x. An example would be that when y equals to cos x plus sine x, dy dx equals to negative sine x plus cos x. The chain rule, where if y equals to fu and u equals to gx, then dy dx equals to dy du times du dx. An example of this rule would be when y equals to 2 sine pi x, dy dx equals to 2 pi cos pi x. The power of a function rule can also be applied when y equals to cos cube x. dy dx equals to negative 3 sine x cos square x. The product rule can be applied when y equals to t cubed cos t. When this happens, we follow the product rule, which is y prime equals to u v prime plus u prime v. Hence, the final answer is t square bracket 3 cos t minus t sine t bracket. Now, by using the knowledge of derivatives of sinusoidal functions, we can apply our knowledge in solving an application question. Here is an example of an application question. A power supply delivers a voltage signal that consists of an alternating current component and a direct current component, where T is the time in seconds, the voltage in volts, at time t is given by the function Vt equals to 5 sine t plus 12. The question A. Find the maximum and minimum voltages. At which times do these values occur? B. Determine the period t in seconds, frequency f in hertz, and amplitude A in volts for this signal. The answer can be found when Vt is differentiated, which results in the answer 5 cos t. Equate 5 cos t with 0 and find the t value. T happens to be pi over 2 and 3 pi over 2. To determine these are maximum or minimum points, substitute pi over 2 and 3 pi over 2 into Vt. Then the results are when t equals to pi over 2, the answer is 17. And when t equals to 3 pi over 2, the answer is 7. Hence, it is a maximum voltage at 17 V when t equals to pi over 2, and it is a minimum voltage at 7 V when t equals to 3 pi over 2. The period can be identified because it is the time required for one complete cycle of a sine graph, which is 2 pi. To find the frequency, we use the formula f equals 1 over t and sub t with 2 pi. Hence, the frequency is 1 over 2 pi hertz. To find the amplitude, we can halve the difference between the maximum and the minimum values. Hence, A equals to half bracket 17 minus 7 close bracket, and this answer is 5. Rate of change exists everywhere and can be applied to almost anything other than sinusoidal functions. Rate of change can also be determined by graphing an exponential function. The Leibniz notation can also be applied when trying to find the instantaneous rate of change of an exponential function. The inverse of an exponential function is a logarithm function. The natural logarithm of x is defined as ln x equals to log ex. The derivative of y equals to e to the power x is still e to the power x. Y equals to b to the power x is an exponential function, and the derivative of the function is b to the power x ln b. An example of this is when y equals to 2 to the power x and the derivative of the function equals to 2 to the power x ln 2. Hence the final answer is 2 to the power x times ln 2. To form an equation of a tangent line, the exponential function must be differentiated and substitute the unknown constant with the value given to find the tangent. From there, integrate y minus y1 equals to mx minus x1 and substitute the values that has been given and form the equation. Differentiating exponential functions requires various rules, and these rules are the same as the rules for differentiating sinusoidal functions. The product rule can be applied when y equals to x e to the power of x, and the derivative of the function is x e to the power x plus e to the power x. The chain rule can be applied when differentiating this function y equals to e to the power of 2x plus 1, and the derivative of this function is 2 times e to the power of 2x plus 1. To apply the sum and difference rule, we can differentiate the function y equals to e to the power x minus e to the power negative x, and the derivative is e to the power x plus e to the power negative x.
Now, by using the knowledge of exponential and logarithmic functions, we can apply our knowledge in solving an application question. The population of a bacterial culture as a function of time is given by the equation p bracket t close bracket equals to 50e power of bracket 0.12t close bracket, where p is the population after t days. Question A. What is the initial population of the bacterial culture? Question B. Estimate the population after 4 days. And question C. How long will it take for the population to double? The answer for question A is the initial population of the bacterial culture is 50 from substituting 0 into T from the equation given. The answer for question B is 225 bacteria. Last but not least, the answer for question C is 5.78 years.
Applications for sinusoidal functions can be found in our everyday lives. For example, voltage signal of a power supply, the simple harmonic or the damped harmonic motion of a pendulum, and the Ferris wheel. Other than that, the decaying of a radioactive substance, a pendulum, and the increase or decrease of population are just a few examples of how exponential and logarithmic functions are related to our everyday lives. One common application that the three functions have is the motion of a pendulum. As we can see, calculus has a huge impact in our everyday lives. Whether in architecture, engineering, or even business, calculus can be found useful in those fields. For an instance, calculus can be used to calculate the profit of a company, whether the company is making losses or earning money. It is important to have a good knowledge in calculus, as it helps us to understand more about how and why a certain thing or situation works the way it does. Therefore, calculus is a crucial subject to teach in school, as it will be beneficial to students. In the future, we hope that more inventions will be created with the knowledge of calculus, and more research on calculus can be done, as until now, there are still some theories in calculus that are still not proven yet. The world needs to understand the importance of calculus in order for a country to grow, whether in technology or in economy.